It's a pleasure to be back here for the second year. This time I was Chris asked me to give a talk on non-volatile memory, but I'm not sure if this is really classical, as Stefan put it. I'm going to talk about some in-memory computation aspects of it also. And I think this will have synergy with some of what Steve talked about, because things are getting, computation and memory are getting closer to each other today. And we may want to start thinking about doing things inside the memory chips as well, which may benefit a lot of other things in the world. Okay, I was here last year. I gave an overview of the memory scaling problem. I'll briefly talk about that and skip some parts that I talked about earlier and then go into non-volatile memory. But I'll talk about main memory. It's a critical component of all systems that we design today. It must scale in many dimensions: size, technology, efficiency, cost, and algorithms we use to manage it if you want to maintain the performance growth and the technology scaling benefits. And regardless of whatever you attach to it, FPGAs, GPUs, this is a bottleneck. And we're designing systems today. Most of the systems are really dedicated to storing and moving data, do the calculations, and most of the system is really interconnect, data storage, main memory, caches. Computation is a very, very little part of the entire system. And there are some recent technology, architecture, and application trends that lead to some new requirements from this system and exacerbate the old requirements. We always demanded a lot from this system. We're going to demand more. And unfortunately, DRAM and memory controllers, as we know them and as we design them today, are already having difficulties in satisfying these requirements. And there are some emerging memory technologies that happen to be non-volatile that enable new opportunities, like storage and memory merging. We'll see if we can get to it. Given this, I believe we need to rethink the entire main memory system and the systems we design around it, because we're really designing systems around the main memory system today to tolerate latencies, for example, to fix the issues we're having with the memory, DRAM, and enable some of these emerging technologies while satisfying all the requirements. Well, let me give you a quick overview of the major trends that are affecting main memory very quickly, and then we'll talk about some problems, and we'll see how much we can cover. I was given 20 minutes, but I'm not sure if I can cover everything related to even non-volatile memory in 20 minutes, let alone memory. Okay, there's an increasing need for memory capacity, bandwidth, and quality of service. This is in all application domains, all systems that we see today. This is not going to change, in my opinion. It's going to become even more. Steve showed digital genomics, for example, as one of the key technologies that was present in all of those different reports. And that's an area where things are growing amazingly. And this is one example of the gap we see between computation and memory. Basically, this is from a paper that was published by HP Labs and University of Michigan in ISCA 2009. They basically show that DRAM is not keeping up in terms of capacity with the core count. And you can argue with this in many, many ways, but it's clear that as we keep adding accelerators into the system, we're not putting enough memory into the system. And if you actually do the calculation for memory bandwidth per core, that's actually much worse. I'm going to save the time and not talk about that. Second trend, energy and power is a key system design concern. This was true in 2003 when IBM published this beautiful paper where they analyzed the energy consumption in their servers. This is true in 2015 in GPUs, 40% of the power in DRAM. And this is data from IBM Power 8, where they also show that 40% of the power is in DRAM. And DRAM consumes power when it's not used, periodically refresh it. And this is one of the big issues of scaling the DRAM technology into the future, which we're having problems with. Basically, DRAM technology scaling is ending. It's becoming very difficult to reduce the size of the circuit reliably while maintaining the beautiful things that technology scaling has provided us with: higher capacity, lower cost, and lower energy. And this is another view of it. Basically, there's increasing cell leakage current, reduced cell reliability, increasing manufacturing difficulties. And I talked about that last time. I'm not going to harp on it this time as much. But there are emerging memory technologies. And broadly viewed, 3D stacked DRAM is one of those technologies. It has advantages, as you can see over here. Reduced latency DRAM, which we've been working on, is another of those technologies. Low power DRAM, and non-volatile memory, which will be the focus of this talk later on. Unfortunately, it's not always green over here. You have reds as well. And I'm going to talk about some of those reds, and I'll talk about how to combine these different technologies to get the best of both worlds, hopefully. So let me quickly give you an overview of the memory scaling problem, since we don't have much time. I'll not harp on this as much. But the basic problem is we're having problems with the charge memory. It's difficult to place and control charge. This is true with flash, although flash vendors have gone 3D, which has enabled them to scale better. This is much, much more true with DRAM today, and that's exactly why we're having problems with DRAM. Capacitor charge is leaking, transistor is causing leakage, and reliable sensing has become difficult as charge storage unit size reduces. And I'll skip this basically. As you reduce the size of the capacitor and access transistor, you get problems. And we've done a lot of studies in terms of DRAM reliability. This is data that we've collected in Facebook servers, and DRAM reliability is essentially reducing. And you can see more in our paper. I'm not going to go into it in detail here. And we've actually built a lot of FPGA-based infrastructure to study these DRAM issues. This is one example. This is another example, and we've open sourced this. You can actually take this and have an FPGA. You can actually do the studies yourself. We put a lot of data out, and this is the latest one. And you can see the publication that talks about that infrastructure. And we've shown that DRAM actually has seen scaling problems. You can predictably induce errors in existing memory chips. This is the row hammer problem. It leads to system security vulnerabilities because you can now flip a bit that doesn't belong to you as an application. You can flip a bit that is in your page table, and you can get access to the entire memory. And I talked about this last time, so I'm not going to talk about this again. So what can we do about it? Basic Industry is also writing papers about it. This is a beautiful paper about from Samsung and Intel that basically argues that DRAM process scaling is getting difficult, so we should put controllers and memory close to each other and have the controller hide the deficiencies of memory. OK, I'm going to skip the slide over here. We have, I'll talk about the solution directions in a little bit. So what are the solution directions that we can take from this? Last time I talked a lot about new memory architectures. It is in the context of DRAM, but I believe it's very much applicable to non-volatile memory as well. So I'm going to touch upon this very briefly, and then I'll focus most of the talk on the emerging non-volatile memory technologies. So we need new memory architectures. We cannot keep doing DRAM as usual. But this means that we believe we need more memory-centric system designs. This leads to new memory architectures, new interfaces, new functions. DRAM is today a dumb device, and we're not even managing waste really well. There are many key issues over here. We need to enable reliability at low cost. High capacity comes from this. We need to reduce energy, improve latency and bandwidth, reduce waste, enable computation close to data. Last time I focused a lot on this one. I'm going to give you an update of that enable computation close to data very quickly. Basically, this is actually, I quickly looked at Steve's report, not his report, but the report to President Obama on the emerging technology. One thing was analog computation, and I believe that there's a huge potential that's not exploited yet. And we've been looking at supporting in DRAM copy, 0, and, or, not, and majority, bitwise operations by exploiting the analog computation capability of DRAM at very large granularities. Basically, you can activate multiple rows to do computation without adding logic. You can add DRAM rows, but no logic inside there. And we've shown that you can actually get significant performance and energy improvements. And we have an upcoming paper at Micro that explains how to do this. And I believe new memory technologies enable even more opportunities. Memristors, resistor RAM, phase change memory, STT RAM, they all have the capability to operate on data with minimal data movement. In fact, DRAM is not the best technology because when you access the data, you destroy the data, whereas the non-volatile memory technologies, you don't destroy the data. You can actually really, truly operate in place. Let me give you an example of the benefits that you can get in the throughput of bulk bitwise operations on various systems. These are some not so state-of-the-art and some state-of-the-art systems, but basically the throughput in terms of giga operations per second in bitwise operations is very low today. If you go to 3D stacked memories, you get some orders of magnitude. And if you go to truly in DRAM computation and combine it with 3D stacked memory, you actually get significant orders of magnitude. This is 2 teraops per second with a single DRAM module, if you actually do it that way. And this is the energy benefits that you get with different bitwise operations. Basically, not energy reduces by 60x, XOR, XNOR reduces by 25x. And you can combine these primitives to actually get a truly functionally complete system. I'm not going to talk about this in detail, but a lot of the concepts here can be applicable to non-volatile technologies as well. And 3D memory provides a lot of other benefits, which I'm not going to talk about over here. So let me go to the topic of this talk, since I was asked to talk about really non-volatile memory. Let me talk about this a little bit. Again, the reason why these emerging technologies are interesting is because charge memory is running out of steam. Scaling it is difficult. And some emerging memory technologies are more scalable than DRAM because they're resistive. And they're also non-volatile on top of this. It's not necessarily combined with each other, but there's an interesting combination. One example is phase change memory. In phase change memory, you store data by changing the phase of material, and you read the data by detecting the material's resistance. This is actually really old technology. But it's become interesting because there's been developments in terms of the read devices that we have for this technology, especially from IBM. And it's expected to scale to very low nanometers. This is old data. It actually goes down to 4 nanometers. Today, we're at 18 nanometers in DRAM to compare. and it was prototyped by IBM at 20 nanometers. And you can actually store multiple bits per cell by dividing the resistance levels into multiple ranges. The problem is, many of these emerging memory technologies have shortcomings as well. Can we somehow enable them to replace, augment, or surpass DRAM? I'll single out 3 technologies that I understand more than others, that I've studied more. We've been working on PCM for about 10 years, a little bit over 10 years, actually. PCM is interesting, and I believe the Optane chip that Intel has right now is PCM, although they never publicly acknowledge that. You inject current to change material phase, and the resistance is determined by phase. STT-MRAM is also interesting. I'll briefly talk about that later. You inject current to change magnet polarity, and the resistance is determined by the polarity of the magnet. And memristors, RRAM or ReRAM, they all have different mechanisms, but one mechanism is you inject current to change atomic structure, and the resistance is determined by the atom distance. And you have very different read mechanisms for all of these. Let me talk about PCM, since we have studied this more within the context of the system. Basically, this phase change material exists in 2 states, amorphous and crystalline. It has different properties. As you can see over here, it's used in rewritable CDs by taking advantage of the different reflexivities of different states. And you can reliably switch between these 2 different states, crystalline and amorphous. And this is how you do it. I don't have time to go over it, but you can look at the slides, which will all be available. And people have shown that you can actually have reliable states. You can actually have different levels in terms of resistance, because the resistance range is very large between the 2 states, as you can see over here. So what is the opportunity? The scaling is better than DRAM and flash because it requires current pulses which scale linearly with feature size. And you can read our paper. You can also read this Rao paper from IBM Journal and Research of Development. It can be denser than DRAM, as I mentioned. You can store multiple bits per cell in addition to the scaling property. It's non-volatile. You can retain data for a long time. And no refresh needed. Refresh is one of the key scaling problems. The paper that I mentioned from Samsung and Intel puts 2 refresh-related problems at the top 2 problems in scaling DRAM into the future. Retention is becoming much more difficult in DRAM. So let me give you a historical overview very quickly. Basically, when we started, we first looked at prototypes that were generated by different academic and industrial institutions of phase change memory. And we did the study where we surveyed the prototypes and tried to derive parameters for PCM for a feature size of 90 nanometers. And these are the papers which you can look at. And this is a very tough thing to do. It's a tough thing to do even today. These are basically different works. These are basically different properties of the PCM devices. And you see a lot of unknowns over here because people don't report those, or they truly don't know those sometimes. And we tried to derive these parameters. Basically, at the architectural level, the pros over DRAM, you get better technology scaling. You're non-volatile. You have low idle power. Unfortunately, cons are actually pretty severe. You have higher latencies. You have higher active energy. When you access, you get higher active energy. Especially for writes, you have 50x higher energy for our averaging, if you will. And you have lower endurance. Basically, a cell dies after 10 to the 8th writes or so. This is similar to flash, except flash is much more severe in this case. And I'm not going to talk about the reliability issues. All scaled memories will have reliability issues, and you'll need mechanisms to correct them. Even in DRAM today, where manufacturers are adding error correcting codes inside the DRAM chip. So there are challenges in enabling phase change memory as DRAM replacement or helper. We need to mitigate the shortcomings, and we need to find the right way to place PCM into the system. And this is our cartoonish picture from circa 2008 or so, basically. And I still like this because it's still relevant. Basically, we thought that that was the dominant system of the today. Initially, we would move to hybrid phase change memory and DRAM systems that look like this. And in the long run, maybe we would move to this aggressive system that replaces DRAM with phase change memory. And we examined this, but I'm going to talk about that later on. This is the first study we did. Basically, we assumed some parameters, and we plugged them in. The parameters are similar to what I've discussed over there. And we replaced every single DRAM cell in the system with phase change memory cell. And the results don't look good. Basically, you get 60% performance degradation, 120% energy increase, and your memory dies after 500 hours. So there's a problem. So you can try to fix the problem by architecting the PCM chips, which I'm not going to talk about in the detail. You do a lot of re-architecting inside the chip. Basically, the key takeaway is if you have a technology like this, you don't want to access it. You want to use it as storage, and you want to do a lot of caching around it. If you do that, the numbers become better. Basically, you get 20% performance degradation. Energy becomes on par, but take this with a grain of salt because all energy numbers are suspect until the technology is there. Average lifetime improves. The problem is, worst case lifetime is much shorter. You can have an attacker program that basically attacks, and you need to have defense mechanisms for this. Intensive applications see large performance and energy hits, and maybe we use optimistic PCM parameters. I'm not sure about that still. And the paper is out there, so you can judge it for yourself. And we wrote another paper combining with multiple folks that are doing similar studies, and you can take a look at that as well. Let me quickly dive into STT-MRAM, because I think that's very interesting also, but that shows you the interesting part of memory technology. STT-MRAM is interesting. It's magnetic, and this was actually one of those other things that was in the president's report, magnetic memory. It has a magnetic tunnel junction device. You have a reference layer, you have a free layer. Reference layer is fixed in magnetic orientation, and you can change the magnetic orientation of the free layer to change the logical state of the device, because the orientation of the free layer with respect to the reference layer determines whether you have high versus low resistance. Okay, you can read and write mechanisms that are reliable, basically. Pros over DRAM are very similar to phase change memory. Cons are much better. We have higher write latency, higher write energy. Read latency and read energy are actually very good. The problem today is the poor density. The size of the STT-MRAM cell is huge compared to a DRAM cell, and it's not clear if we're going to reduce it to a level that gets to the small cell size we have with DRAM in the next 20 years or so. We'll see. But it's very interesting. Actually, it's maybe even more interesting for replacing on-chip SRAM caches. But we did the study to replace DRAM with STT-MRAM, and we found out that if you do the proper architecting, if you do the proper buffering, you get very close to DRAM performance, about within 10% of DRAM performance, and you get significant energy savings, although take that with a grain of salt again. Okay, there's more in this paper. I believe going forward, a much more viable approach is something that looks like this. None of these technologies have good characteristics that are better than DRAM. They all have greens and reds. So if we combine different technologies that have different types of green and reds, and design the hardware and the software to manage the data allocation and movement to achieve the best of multiple technology, we can do much better. So I think a huge challenge and opportunity going into the future is providing the best of multiple metrics with multiple memory technologies, not a single memory technology, which leads us to heterogeneous, configurable, and programmable memory systems. So there are many issues over here. I'm going to touch upon a few of these as much as time permits. Basically, do you use some of these as caches versus main memory? What is the granularity of data movement and data management, fine or coarse? Who manages it? Hardware, software cooperative. When do you migrate data? How do you decide that between the different technologies? And how do you design a scalable and efficient large cache? And you can probably add more to this. Let me talk about a couple of these. Data placement is a problem. Basically, you have, even if you don't have non-volatile memory, you can actually design different types of DRAM over here. And you need to be judicious about how to move the data, especially if you're moving large pages. And there's another issue. Load should be balanced across both channels. If you actually utilize this channel very well, this channel may become idle, and you may actually have a worse system balance than before. OK. Basically, I'll give you a little bit more historical overview also. A lot of people have looked at this problem. When we started, we looked at characterizing data access pattern and guiding data placement in hybrid memory. And the key idea was very simple. You figure out what accesses are streaming. Streaming accesses are as fast in phase change memory as in DRAM, so place them in phase change memory. In fact, if all you're doing in the system is really streaming, maybe you put your data in tape and you do enough buffering in the system and stream through the system, right? But random accesses are much faster in DRAM, and that's where the fast technology wins. So we would like to be able to categorize these accesses and place them, place, of course, some random access with some reuse in DRAM and streaming data in PCM. So if you do that, you actually do reasonably well. You get in between. This is 16 gigabyte PCM performance. This is 16 gigabyte DRAM performance. There's a huge gap here because these workloads are actually extremely memory intensive. And if you do the management that I suggest, you get somewhat in between. You don't get as close to DRAM. But maybe you can argue that this comparison is actually bad for PCM because maybe PCM should be 64 gigabytes over here. OK, very quickly, I'll give you one more example. Basically, I think a more comprehensive solution is better going forward. I'll give you some recent work that we've done. Previous work uses heuristics, including our work, that are a limited part of the memory access behavior. They do not directly capture the overall system performance impact of data placement decisions. For example, none of them capture memory level parallelism. I'll give you an example over here. Basically, if you have this memory access, if you migrate it to fast memory, you win because this is the only memory access that are blocking the system. You reduce the stall time directly. But if you have concurrent memory accesses, if you migrate only one of them, you don't win anything because you need to really migrate both of them to the large memory to be able to reduce the stall time. So if you're not aware of the memory level parallelism in your migration policy, you may migrate to only one of these concurrent accesses and gain nothing in terms of the system performance benefit. That's what we did in our recent work. We had a generalized mechanism that directly estimates the performance benefit of migrating a page between any two types of memory and place only the performance critical data in the fast memory. And I'm not going to talk about this in detail. You can read the paper, but I'll give you some results over here, and then I'll conclude. Basically, we've compared this to various different mechanisms that manage hybrid memories. And it turns out, and the more interesting parts are always the memory-intensive workloads. Less memory-intensive workloads, you don't gain anything with most of these memories. But with the memory-intensive workloads, if you actually directly estimate the performance impact of migrating a page to the fast memory versus the slow memory, you can get significant performance improvement. And for these memories, you never know what kind of latency characteristics and bandwidth characteristics you get. So it's always good to vary the latency multiplier and bandwidth multiplier. And it seems like the mechanism performs reasonably well compared to the best previous mechanism, regardless of the latency and the bandwidth characteristics that you have in the in the slow memory versus the fast memory. Okay. So basically, the challenge and opportunity is to enable an emerging technology to augment DRAM. I'm not saying replace DRAM at the moment over here, because it's going to be a long way to replace DRAM, in my opinion. And this means that we need to manage hybrid memories very well. And another challenge is designing effective large DRAM caches. But since I don't have time for that, let me go to the conclusion over here. But these slides will be available, so you can take a look at that. Okay, maybe since I have a few more seconds over here. So this is what I didn't talk about. I think we have the other approach to take advantage of these memories is to take advantage of the persistent properties at the program level. I think that requires a lot of programmer support to be able to do that. And we've been looking at mechanisms to do that, but I don't have time to talk about that. This is one example, work that we've done with VMware, but you can take a look at that. Let me conclude, I think. I think the future of emerging technology is very bright, even though I made it sound like some technologies are not there yet. Regardless of the challenges in underlying technology and overlying problems and requirements, we need to research them, because they can enable orders of magnitude improvements in different things. And they can enable new applications and computing systems. But of course, we need to think across the stack. I mean, actually, all of the solutions that I've talked about require some sort of across the stack thinking, software, hardware cooperation. And we need to design enabling systems. If you're in doubt, I always get this question, so I'm going to try to preempt this question. Like, will any of these technologies be ever available? You should refer to flash memory. It was a very doubtful emerging technology, let's say 20 years ago, for at least 2 decades, actually, when it was developed. But we're today using it everywhere, right? In fact, there are amazing things that are going on into the flash memory technology to make it work. The technology itself has a lot of flaws, but the controller that we designed for SSDs actually make the flash memory work really well. And we've been doing a lot of work. You can take a look at the recent work that we've done on that summarize a lot of the work in error characterization, mitigation, and recovery in flash memory-based solid-state drives. And decades of research has enabled this type of technology to be everywhere. And I believe decades of research will be required for other technologies to come into use in a widespread manner as well. Okay, thank you.